And my supervisor is Dr. Arasti. I'm going to start with introduction, how to utilize the distribution system, and after we have a problem statement, solution approach, including 3 different levels is next, and we have 2 numerical examples for verification and 1 example for validation. Also, I'm going to introduce a specific software which is designed based on the solution approach for software section, and at the end we have a conclusion and future work. Into the competitive business world, most of the companies they are looking for better business market and generating income by controlling costs and improving the quality. As we all know, in these days, so many companies they focus on the eastern countries, especially China, for the production, and the reason is the different and huge difference of the cost of production. By a statistic, the average salary in North America for factory worker is between $35,000 to $55,000, but at the same time we have a several times lower in eastern country. So in such a condition, having an efficient and optimized distribution system of food can play a vital role for the companies in terms of the cost controlling and income generation. And any kind of slack in distribution system is the cost of the lost profit and customer. Food distribution is also an essential part of the business activity in supply chain network. In the other hand, we have 2 main factors. One is transportation, and second one is food distribution. For companies that are responsible for negative environmental impacts such as traffic, such as congestion, pollution, noise, and so on. But the question is, for having a good distribution plan, what exactly we need? We have to answer some questions. First, we have to know how many vehicles we have to use, how many terminal or depots we need, how good should be distributed, which road should be selected, and which road is the best one. Also, the efficient factor and main factor for distribution can come as a traffic condition, number of people, distribution system, vehicle capacity, cost of operation, and customer satisfaction. So in this thesis, we address 3 main problems. The first one is the client allocation, and second one is the order scheduling, and third one is the route planning. So this problem is investigated in the urban area. Our solution approach is including 3 different levels. The first level is the allocating of the different clients to the depot, and second step is the scheduling the receipt order by the client, and third step is the route planning. For client allocation, we use 2 different algorithms. First, we are using the nearest neighborhood, and after, by using the top search algorithm, we improve the result. Whatever is the result of allocation is going to be the input for scheduling, and by using the genetic algorithm, we are trying to find the best scheduler plan. And also, whatever is the result of the schedule is going to be a result for the route planning, and in the route planning, we have 2 subsections. The first one is the client vehicle allocation, and second was the route planning, and we are using the Digital algorithm for route planning. Also, we have a specific software which is designed based on this approach for a big size of numerical example and in reality for the companies. So the customer allocation is first step of our approach. We have a hybrid approach based on the nearest neighborhood and top search for the allocation. Also, regarding to characters of the urban area, we have a different characters like different factors like time travel, like access delay, time delay, and congestion. They should be considered for the allocation. So we do weighted scoring model to have a unique service time for all of these criteria. The first level in the allocation is the nearest neighborhood. In nearest neighborhood, first we calculating a distance between each pair of the client and depot, and after we are starting with the random of depot and selecting to the nearest client, which is not unvisited for the another client. And also we repeat this kind of allocation until we meet the maximum number of the allowed client per depot. So the next step is the calculation of the objective function. Based on the nearest neighborhood, we can find several multi-different solution, and for each solution, we can calculate the objective function. Whatever is the result of the neighborhood is going to be the input for the tabu search. For the tabu search, we are using the lowest objective value between the solution in the nearest neighborhood, and by using this initial solution, changing the two clients or several clients between the initial solution, you can obtain and make a new neighborhood. And after making a new neighborhood, again we are calculating the objective function, and if the result of the objective function is improved, we are going to add it to the tabu list for preventing another search for future. So also we use in tabu search, we are using a short-term memory, which is a list of the recent solution, and also aspiration criteria is for the solution, then the solution involving in the sub-move, and it has a better objective function in compared to the best known one, so we can disregard the tabu status. The termination criteria for this algorithm is considered as 100,000 iteration or after 15% improvement by solution approach. Also, to making sure the result of our approach, we compare it to other different materialistic methods. We compare it with the greedy algorithm, Ancoloni, and only with the nearest neighborhood. As you can see, the result of the tabu search and algorithm and the nearest neighborhood is better to compare to other solutions. So the second step in our approach is order scheduling. When we are talking for order scheduling, we have to consider some important factors that are affecting the scheduling, like loading time, like historical delay, packing time, access delay time, unloading time, and so on. For having a unique number for these different parameters, we do weighted scoring model, and we can, based on the related weight, we can calculate a specific and unique number and unique service time for each one. And by using these numbers, we're taking a genetic algorithm for calculating and obtaining very optimized scheduling. The first step in genetic algorithm is making a population. Populations can be generated by randomly, and each individual in this population can be called as a chromosome. For example, for this population, we have 6 different chromosomes, and the next step is calculating the objective function for each chromosome. The parent selection for generating the next generation is based on the ranking method, which is picking the best individual based on the objective function value. Also, for crossover, we use the 1 point crossover, which is randomly created 1 point for crossover. And after crossovering, we have a mutation. The mutation operator works by selecting one of the client and allocating to another place. So we calculate the objective function for new generation, for new offspring, and after, if we feel we have improvement in new generation, we can replace it with the old one. And the replacement method is based on the less fit one member. We are comparing with the population and find the lowest one and the less fit one and replace the new generation with that one. Population size for this sample is considering as the total number of the client multiplied by the total number of the default. The second step is route planning. For route planning, we have 2 subsections. The first section is the vehicle allocation, and second one is route planning. For vehicle allocation, we use weighted scoring method, and for route planning, we use the modified Digital algorithm. So for vehicle allocation, regarding 2 characters of the urban area, we have a different parameter. The main parameter is the capacity of the truck, and we have also the noise, and we have the emission and cost of operation. Let's say, for example, for a specific receipt order, for 6,000, we can compare it with the capacity of the truck. We can have 2 different solutions. The solution number 1 is 2 medium truck, and solution number 2 is 1 big truck and 1 small truck. And also by calculating the different factor, cost, emission, and noise, we can see at the end the solution number 2 has a better result in compared to the first one. And so we are using solution number 2 as a vehicle allocation. The second part is the route planning or approach. So we are using the modified jigsaw algorithm. The jigsaw algorithm is usually working based on the shortest distance, but we are modifying instead of the shortest distance, fastest path, and also considering the different characteristics like travel distance, congestion, and other factors. We're calculating the specific and unique service time between each pair of the client and depot, and also we can by the jigsaw algorithm we find which route is the optimized one and is the best. So we have for verification we have two numerical examples. The first example is the including 21 clients, and second one is including 50 clients. This is bigger. In the first one, we are just starting with the nearest neighborhood, and we have 21 clients, and we divide them for 7 depots. As you can see, the objective function from the 85 by nearest neighborhood is improved to 53 after using a top search method. And also for the scheduling, based on the receipt order, we have a different criteria. We have to calculate the weighted scoring for each pair of the client and depot, and use this kind of number for calculation genetic algorithm. And you can see the objective function from 121 is improved to 91. So the total number. So we can see we have improvement in genetic algorithm, and the last step for the sample is the routing. In the routing, we have two subsections. The first subsection is the vehicle allocation for depot number 1. For example, we have two solutions. Solution number 1 is the 2 big truck and 1 medium, and solution 2 is 2 big and 3 small. So as you can see, the solution number 1 is acceptable because it has a lower rate from another one. And for route planning, we use the modified algorithm, and you can see the result from 91 is 78, and there is obviously there is an improvement after using this method. For second sample, we have a 50 clients, and we allocate them to 5 different depots. It means we have 10 clients per each depot. So by using the nearest neighborhood, the total objective function from 6,500 is improved to 6,100 after using the table search algorithm. And for the scheduling, by using the genetic algorithm, the objective function from 6,000 is improved to 5,400. So we can see we have improvement in the sample. For route planning, we have a different solution for different depots. For example, for depot number 1, we have a 3 solution, and for others the same. And for depot number 1, obviously what we select the solution number 1 because it has a lower weight compared to other, and we have the same situation for others. So the second step for routing is the route planning. For route planning, by using the jigsaw algorithm, the total objective function around 5,400 is improved to 5,300, and you can see we have a improvement in the result of the objective function. And also for validation, the client allocation, we took a numerical case studies presented by Django in 2003. Also, we used the nearest neighborhood and table search and run 9,000 iterations for the solution. And as you can see, for that solution, they offer 7 different apparatus solutions, and we use the average of those solutions, and in compared to our result with the average of the apparatus solution, we can see the total shipping cost from 7,900,000 is improved to 6,500,000, and also the total transit time from 124 minutes is improved to 105 minutes. So obviously, solving this kind of problem in the huge number of the client and depot by hand is impossible. So based on the solution approach, we develop and design a specific software which is working based on each step of our solution approach. In the first step, we have a data form for entering the data. We can define different people and client, and for each one we have we can define the position, and also we can have a different project. So the first step is the nearest neighborhood. By calculating distance between each client and depot, we can find the nearest neighborhood for each depot in this form. And also for the top search form, we can see for this sample, so far we have like 25,000 attrition, and also the total objective function is so far for this sample is 7,800, and also it takes 3 hours so far, and the best result so far is this allocation. It's exactly working based on the solution approach by top search. And also we have 2 different forms for the scheduling and for routing. For scheduling, based on the genetic algorithm, we can calculate which scheduling is the best one, considering the total distance. And also we can have different allocation for the vehicle, and also we can calculate it based on the Jigsaw algorithm, which road should be selected and which road is optimized in terms of the total service time. As a conclusion, we address the problem of good distribution planning in urban area, including 3 different levels. The first, we explain the balanced allocation of customers to the logistic depot with the nearest neighborhood and top search. And also, after we do order scheduling of the customer to logistic depot by genetic algorithm, and at the third level, we have a vehicle allocation and route planning of good distribution to the customer by using the modified Jigsaw algorithm and also weighted scoring model. The advantage of this solution approach is ability to deal with the large size of problem and generating fast and good solution for distribution, and also we design and suggest better way of efficient distribution both to the city and considering to the characteristics of the urban area. The limitation of this work is the lack of real-time information from the traffic condition and also the vehicle availability after planning. And also we have covered the last thing in the supply chain network, but in the good scenario, we can develop it for all over the supply chain network. The future work for this project can be in managing the immediate customer demand in routing and scheduling, congestion modeling, and also investigating the application for intelligent transportation system, and also testing and validating the proposed software for the huge number of the plan and in the reality for the companies. Thank you for that attention.
Thank you very much. So we'll go on the next round. So we start with the external examiner. Thank you.
Thank you for your presentation. My first question is, in your thesis, you solved 3 problems: customer allocation, order scheduling, and vehicle routing. The point is that these problems are very well-known problems of industrial engineering. If you Google these keywords, you will find lots of papers. If you might know it, there are many optimization models for that, which you didn't put them in your thesis. That's right. But my question is then, what is the point of just mixing these 3 problems? Is it your, what is the point of contribution of your thesis?
Actually, in terms of the company point of view, for sure we have a different solution for different type of the problem, for each level of this problem. But if you take a look at the point of the company, they are looking for the last solution. They don't care what's the result of the allocation, what's the result of the routing, and so on, the scheduling. They need the solution. They can deliver their goods and they offer their service, whatever is the service of the company. So at the beginning, we interviewed with some companies and considering the problem for this kind of the companies is having a specific plan for the delivery the stuff. from the beginning. So they have, for example, they have maybe several clients in different position of geographical position, and also they have a specific receive order per day or per week, and also they have a specific amount of the facility for the truck and other stuff. So they are looking for to find the solution to how they can deliver it, how they can planning. So it doesn't actually we work based on the point of the company point of view to solve this problem. Is kind of mixing three different problems together.
So you're saying that just mixing these three problems is the contribution?
And take it and look at the one problem including three different levels.
No, because as I said, each problem is an optimization problem.
Exactly.
It's a model.
Yeah.
And you can give the model your parameters, your demand, your geographical information, and it will give you a solution. One point is that, first of all, if you model it as an optimization model, you could have put all the three problems in one single model. So that's the first question, is why didn't you try that? I mean, in terms of optimization, it is feasible too, because you divided them into three sub-problems, but you could have put them in one single model, and for sure the size will be big, but you didn't solve them for optimal, you used meta-heuristics. But I'm saying that, okay, these problems, these models exist, and the algorithms are also exist, different algorithms. So what is the main contribution? I mean, what special thing you did which is different from the literature?
Actually, as you mentioned, there is a different algorithm for each level. So first of all, we use for different level, we use different algorithm and verify or result with the other related research. This is the first step. And second one, so it's obviously we have a different solution for each step. But the question is, if we take a look at from the company point of view, it's not satisfy the company. You know? They are looking for the last answer, and they are looking for have a plan to can serve the good. But for example, offering the allocation system, or offering the scheduling, or offering the routing plan, those companies they can satisfy them. I think my contribution is merging these three together, this problem together, and make one result in terms of different algorithms and different solution for the companies.
So my second question is, your problem is multi-criteria. You have three criteria in your objective function.
Yeah.
And you use three weights, W1, W2,
Yeah.
and W3. So, and it's all about you said in your thesis that you consider access regulation delay, time regulation delay,
Yes.
and congestion delay.
Yeah.
The question is, how did you measure these criteria, and how did you estimate those weights?
Actually, it's part of the assumption of the project.
Okay.
For example, we say based on the nature of the problem, nature of the criteria, like let's say for the transit time, we all know it's an important factor. It's a big part. It can be a big part of the problem. So we put the big size of the weight for that one, and also for the noise and for the other criteria. It can be different for each project. Actually, it's variable. We can define it for different criteria and different weight for each company. It's not the fixed solution. You know, for example, maybe for the company number 1, they have a very pressure, and it's very important to consider the noise for that specific area. But for another company, they don't care the noise because they are working in the rural, they are outside of the city, so it can be comes down, and even it can be zero for the different problems.
So if a company is interested in your work, how are you going to help them to come up with these weights?
We can measure the weight. We can investigate this kind of criteria, how important is for the company, based on the position in the city, geographical position. Let's say the company, they are located in downtown. They are different. They have a different way. In another company, it's located to like the highway or other criteria.
So you mean that if the company should identify these weights, or
they can offer, or we can like sit down and to each other and find it, like a specific and related weight for them.
Okay, for now, that's fine.
Okay, then.
Obviously, we have done a lot of work, and the writing, thesis writing is very good. So, my first question is similar to the external examiner. You have done, you have investigated a lot of problems, right? So,
regarding this problem,
the client allocation, order scheduling, and routing. And in addition to that, you have developed the software,
yes,
right, to implement these methods.
yes,
And for each one of them, you are looking at several algorithms and implement those algorithms. So all of these are time consuming.
yeah.
But still, I'm not very clear about because for master thesis research, you contribute something new to the knowledge in this area.
Yeah.
So, is your key contribution is that divide the problem into 3 levels? Is that your main contribution?
Actually,
you divide the overall problem to client allocation, order scheduling, routing. There's a bigger problem to these 3 levels. Is that your main contribution?
Actually, we break down the one big problem in 3 different sub-problems, and after for each sub-problem, based on
I'm asking you if this is your main contribution or not.
yes, exactly, it's my contribution.
So, in the literature, the current methods have not divided the overall problem into 3 levels.
Actually, in the literature review, we investigate and we find a different related research for each area. For example, we take a look at other researches they have done for the allocation, and then compare it with our solution, and also the same for the scheduling and the same for the routing.
Okay, let's say a company faces the boost distribution planning problem. That's an overall problem.
Yes.
Okay. Now you can divide into 3 levels.
Yes.
So you mean this is your main contribution, and others have not done this before.
Exactly. Can I explain the board? Let's say we have a specific company which is a lot of they have so many clients in the city contracting for the urban area. So let's say there are different clients. First of all, we divide them for different depots. It's the first step of the solution approach for contribution. And after, for each section, let's say for depot 1, we take depot 1 here, and for this one, we try and develop for the scheduling based on the genetic algorithm, by using the genetic algorithm. So we have here, we have a detailed problem, and it's a breakdown problem, second level. And we find that here is like the list of all the scheduling for this specific depot, for sure, let's say for depot 1. And in the third level, by using the Jigistar algorithm, we find which route should be selected, for example, to meet all the client. We break down the one big problem to several small problems to can be like more precise to solving this kind of issues. And also we have the same scenario for other depot and other allocation
Okay,
sections.
so in the current practice,
yeah.
how do people deal with this problem? How do people deal with boost distribution planning? So currently, in the current practice, people do not divide into these different parts and deal with them separately.
In reality, actually, they have different warehouses or different, let's say, distribution system, logistic distribution system. And after, let's say, when they receive a lot of requests from the retailer, let's say, so they send all the order, receive order for those specific the warehouse, and after that one from those warehouse, they can be distributed to the other client. The client means like, let's say, the retail store can be solved.
Okay, what's the advantage of dividing the problem into 3 levels?
We can be more precise because if you want to take a look at the whole project, in the, like,
Why you can be more precise by dividing into 3 levels? I think if you do the, consider everything in one optimization model, it will be more precise.
Exactly. But the thing is, if let's say for a specific company, if we receive several orders per day, okay, and we are in different geographical positions, in different places of the city, if you want to sit down and solving and scheduling all of this receive order by one shot is going to be very harder.
So the advantage is not more precise. It's not more accurate.
It's more accurate, or yeah, it can be like after dividing in separate clusters, can be like, we can say it's more precise because we are not comparing to each other. Let's say if we have one client here and one client here, especially for routing plan, we don't need to like connecting these two together. We know this client only deal with this bunch of the other clients. They are not related to others. I think it's very, it's saving the time for calculation.
So I think the main advantage is it may be more efficient, but it's not more accurate.
Maybe.
Okay. So I'm asking the question, what's, and you can think about it, what's your key contribution? Is your key contribution proposing the framework of dividing the 3 levels, or is your key contribution in each or one of these 3 levels? For example, in the client allocation, right, you look at several methods and compare the performance of different methods.
Yeah. No,
so do you have some contribution there or not?
No, the main contribution is defining the framework, as you mentioned, defining the main framework for this kind of the problem and divide them to different problems can be more accurate. But the thing is,
so for each one of them, for example, for client allocation,
yeah,
do you have some new contribution there?
No, just using like the heuristic algorithm to can find the optimized or near to optimized solution. We don't have any new a heuristic method or new solution for it.
Okay. My second question is, so you have developed some software,
Yes.
To implement the methods.
Yeah.
Who do you think will use the software? If you try to sell the software to some companies, what kind of companies will use your software?
To be honest, the software is not 100% ready for the selling.
Not in the future, after
in the
study.
future, yeah. I interviewed with 2 main companies. The one was the Costco, another one for the Loblaws, and they said they have in the reality they have a manual distributing plan. Let's say, for example, historically they know, the demand of the specific part of the city is higher than the others, and they know the delay time and transit time and whatever the other criteria take 2 hours and 3 hours to deliver for the stuff over there. So if I think we complete the software and test it, and after everything, it should be very interesting for this kind of software because it can be helped and it can be save a lot of money for
Can you give some examples of such companies?
Like Costco, and Costco and Loblaws, both of them. For example, let's say Costco, they have several stores in the city, and they have one main warehouses in the rural area. And after the main company is in the United States, when they receive the order from the different store, they send the order to the warehouse, and warehouse based on the availability or whatever, they send the orders to the client. But if they have such a kind of the.
But in your example, if you use Costco as an example, so that's within Costco.
Yeah.
Within Costco, right?
Yeah.
Between the warehouse and these retail stores.
Exactly. Yeah. Yeah. It's between.
Not between.
The meaning of the client is the stores and retailer to compare to the warehouses and also the factory and the supply chain network. I mean, the client is not the person; it's the the place they are receiving order and they're using the orders.
It's not some other companies, clients?
No, they're the same company, for sure.
Okay.
It's within the one company.
Okay. Okay, next question is for the client allocation, order scheduling, and routing. I think for those sections, I think you focus most on the solution.
Yes.
But the mathematical modeling of those problems are not clear. You didn't provide a clear description of the optimization models.
Mathematical, that's right. Because we are using actually the current meta-heuristic method, and
but we need to know the models first before presenting the solution.
yeah, that's right.
So I think for each one of them, you should add those optimization models and clearly formulate what's the object function, what are the design variables. Okay, that's all.
Supervisor?
I will ask one question to you is, can you tell us about what is the, when you say your problem is able to deal with large size problem sets, how large is the problem? What is the maximum? And do you have some ideas about it? Is it 100? How large can the problem be?
Actually, let's say for solving the problem with the 6 client, 10 client, or even 50 and 100, it's very easy to handle it with this solution approach. But when we have in the reality, we receive 1,000 order and 1,000 client, and also the decodes, it can be very confusing and it can be very time-consuming in terms of solving the problem. I believe based on the proposed software, we can solve even to up to 500 clients. And the other side is depends to the structure of the database and other related stuff.
Now my second question is that you propose some literature review in the thesis. In literature, how many studies do you think have addressed excess timing, sizing regulations and related congestion conditions for goods distribution? How many works have addressed these types of problems?
Actually, there is so many paper and there's so many research in the area of the allocation and scheduling and routing. They are very well-known problem in the industrial field, but the thing is it's very less attention to considering the urban area characteristics. And most of them, they focus on only working with the distance and only working with the one parameter instead of considering the other effective, the factors related to cities and urban areas.
Now my last question to you is, you say that you have your contribution is different levels of the bigger problem, and for the different solution approaches, you are proposing, let's say, nearest neighbor and taboo search algorithm. Are they already being used by other authors to address the customer allocation problem? Is nearest neighbor and taboo search already used by somebody else?
No, they don't mix these two together. At least I didn't find any related research to have this mix of these two meta-heuristic methods. So many of them, they like using the ant colony, they use the greedy algorithms, they use the genetic algorithm and other things, but we mixed these two together and compare our result with the other, and we proved it's improving, especially with for validation compared to the papers.
So is this your contribution?
Yeah.
But you should tell when Khabbazian asked that you also propose.
Yeah.
Sure.
Thank you for mentioning.
Okay, thank you. So the second round?
So for the last problem for vehicle routing,
Yes.
you use the Dijkstra algorithm, which is the shortest path algorithm.
Yes.
Have you heard about traveling salesman problem?
Yeah, I read a lot of problems for this area because it's very close to each other.
My question is, why didn't you go for traveling salesman problem? Because you have a tour,
Yeah.
the vehicle starts from a point, it needs to ship the goods to different points and get back to the same
It's
depot.
a round trip, let's say.
So why didn't you use, because usually in traveling salesman, the point is that the truck shouldn't repeat any node in the network.
Exactly, they have to
So
walk
it should be one single round without any repeating any points. So the question is, why didn't you go for this method? Is there any reason for this problem?
No, actually, there is a lot of, let's say, software, and there is a lot of paper for travel sales TSP problems, actually, as you all know. But the thing is, in Thesis, we try to find another solution, or at least try to another algorithm to see what's the difference between these two. If we like to follow the current and exist the solution, which is very famous and well-known problem, I didn't find any point to follow exactly the same thing. Maybe other professor like Dr. Tian asked me what's the point of following and using this current and the poor solution.
But Dijkstra is a very well known. Everybody first understands Dijkstra, and then the people understand
yeah, but at least it can compare.
And you didn't compare them together. Did you compare Dijkstra to traveling salesman?
No, we didn't.
So you're saying I wanted to. If you say I want to use another method, the good
we just
thing
use one. We just use one of the solution for routing, and we feel like the Dijkstra is maybe is best fit for this kind of problem compared to also TSP, and also TSP there is so many research on it, but for the Dijkstra is less attention and compared to TSP maybe.
I guess because Dijkstra is a simple problem and there is nothing to do research on that, because it's another problem. Dijkstra is only you want to find the shortest path from point A to point B, no matter how many times you visit one node in the network. But in the traveling salesman, you need to visit every node one single time.
Okay, as I mentioned, we modified the Dijkstra algorithm. We have two changes on it. The first one is that instead of the shortest path, we are calculating the fastest distance, and also another one is we have an assumption we are not allowed to visit 1.2 times. It means when, and we have another assumption when we are, let's say we are moving from point A to point B. Let's say we have a different position here. We start over here, we meet this point B, and after the assumption is that we cannot repeat this point first, and second one is we have to start from the B.
I know very well the Dijkstra algorithm. That's fine. I just ask, is there any reason that you use it for this thing? Okay. I can say I don't have more questions, but I have a few points because I asked you about the weights that you use, W1, W2, and W3. Thing is that in reality, it's really hard to find values for such weights, and based on what Dr. Alasi is saying, is one of the contributions of your thesis that you consider these three criteria in the objective function. So to me, at least, you could have done a sensitivity analysis to see what is the effect of changing such weights on the different solutions of different sub-problems. I don't know, maybe you can add it in future work.
Maybe it can be future work.
Yeah, but it's a good thing that for whenever you have goal programming, that's not the best way that you did. For goal programming, we have constraint methods, find non-dominated solutions for different criteria. So at least I believe you could mention it in the future work that more sophisticated methods of goal programming can be applied to this problem to really, because there is always should be a compromise between different criteria. These criteria are not in line together, they're conflicting, they're competing with each other. So a sensitivity analysis, and after that doing a more sophisticated method like epsilon constraint method, something you can add it in future work, you can improve this work. That's the suggestion. The other thing is that you only try to validate the first algorithm, taboo search, for customer allocation. The other genetic algorithm for order scheduling is not validated. You didn't compare it with another algorithm like ant colony or something else, which is okay. You didn't do that, but at the same time, you didn't evaluate your algorithms in terms of times of finding the solution. If you say that is going to be applied in real industry. So the time of coming up with a solution is really something really important. So working at this part to see how efficient you are, because to my knowledge, when you use meta-heuristics, you need to run them for several set of parameters. You didn't do that. You just said we consider, I don't know how you say if you have 15% improvement in the objective function, why you say you should stop, or why you say after 9,000 iteration you should stop. What people do, they change the value of these parameters, they repeat it for different set of parameters, and after that they can say that this algorithm is an efficient one. That's something you didn't do it in, and you don't know your software is fast, it is too slow. So that's something else maybe in future, especially if a company needs to buy such a software, they need to make sure that the engine is working well, which are those three algorithms. That's all. That's
Thank
my
you very much.
comment.
Thank you very much.
Thank you.
No, I don't have any questions, but maybe if you have your thesis with you, you can highlight the computation times. Or
Yeah,
different, or
exactly.
maybe you can
We have-
answer to Dr. Khabbazian.
for sure, yeah. I do have that.
But do you have it with you right now?
Yeah, it's on.
No, it exists, but it is not